So in chapter 4, we're going to talk about polynomial functions. And polynomial functions basically have this general form. But let me, better than this, let me give you some examples of some polynomial functions. So p of x could simply be 2x squared plus 3x minus 4. Could be px equals 5x to the fourth minus 2x squared plus 1. Px could be 2x minus 7. Px could be, 10x to the 7th minus 3x to the 4th plus negative 3, something like that. These are all examples of polynomial functions. So let me point out a few things that are not polynomial functions. So if you look at this, notice that all of the exponents are positive integers. So you must have positive integers. The integer here is 1, remember? So you must have positive integers. You also cannot have decimals, fractions, negatives, square roots in the exponent. So the exponent cannot be anything but a positive integer. And let's look at some of the graphs. So let's page. So if we have a graph of a polynomial function, basically what you're going to have is you're going to have a line going off to infinity in some direction, could be any direction, and then in the middle you're going to have a whole bunch of bumps going on. So we're going to have a bunch of bumps going on here in the middle, and then we're going to connect those two. So these two, pretend those two are connected, and those two are connected. So, and now those graphs can be going in any way. So I could be going off to infinity in both directions with a whole bunch of bumps going on here. Sometimes they cross the x-axis, sometimes they don't. So I could have, maybe it's going off to infinity here and here. Oh, actually that one is going to cross the x-axis. Let me give you one that's not crossing the x-axis. I could be going off to infinity here and here with my bumps all happening here. So the general gist that I want you to get from what a polynomial function that's very important is that on both ends, look at the two ends, and we're going to talk about end behavior in a minute. As we look at the ends, we've been putting arrows on the ends of our graphs since you learned how to draw a graph. And we've been putting those arrows because it means it's going off into, out into infinity, right? So it is important that with a polynomial function, we are either going up into positive infinity or we're going down into negative infinity. Sometimes they're both going up to positive infinity. Sometimes you have a mix. You have one going up to positive infinity, one going down to negative infinity. And we'll talk about all of that in a minute. That's called your end behavior. So let me show you some graphs that are not polynomial functions. So some graphs that are not polynomial functions. So let me write that really big. These are not polynomial functions, so let me give you some examples. Okay, so a function, first of all, that's disjointed. So if I have a graph, remember our piecewise graphs, even if they do go on, even though this is going off to infinity and infinity, if there's any kind of a gap in the graph, it is not a polynomial, so there can be no gaps. It also, like I said, does have to be going off into infinity. So if I have like a graph that looks like this, that is, because this is going to continue to repeat, it's going to continue to go back up. This is not a polynomial function because it's not eventually going up or down into infinity, right? This just kind of keeps bouncing around. I also cannot have any sharp edges in my polynomial function. So I can't have an absolute value graph. That is not a polynomial function, so there can be no, actually that's a bad graph, sorry. Let me redraw that one. So let me put my line back on there, sorry. Oops. Okay, so this, the absolute value graph, if it has a sharp point to it, this is not a polynomial function. And it also has to go, a graph like this is not a polynomial function. Okay, the domain has to be all real numbers, and this domain is not all real numbers. Okay. Let's talk about turning points and zeros. So if we have a polynomial function, let's say p of x equals 3x to the fifth plus 2x minus 7. This is a fifth degree equation. If you remember, the highest exponent the highest exponent is 5. So this is a fifth degree equation, which means it has at most 5 zeros. So it has at most, it doesn't have to have all 5, it could only have 3, but it has at most 5 zeros. And the word zero is the same thing as an x-intercept. It's also the same thing as a solution. And it's also the same thing as a root. So all of these words are synonymous, but in this chapter, we are primarily going to use the word zero. So a zero is where it crosses the x-axis. So at most, it will have 5 zeros. And turning points, remember those bumps I showed you? So the turning points, so that's how many bumps it has. I'll write the word bumps. Is going to be at most n minus 1. So if we call 5, our n value is our highest exponent, it's going to be 4 in this case, because 5 minus 1 is 4. So let me do another example. So let's say, okay, so let's look at an example of a function. So if we have p of x equals 3x cubed minus 2x squared plus 4x minus 7. If you notice, this guy has a third degree. So this is a third degree equation. The highest exponent is 3. So it is going to have at most 3 zeros. And it's going to have at most 2 turning points. Or let's just say 2 turns. Those are the bumps, remember? So it could have 3 zeros, it could have less than that, but at most it's going to have 3 zeros. Okay. It also, I want to point out that it doesn't matter. Let's do another equation. P of x equals negative 3x squared plus 4x to the 5th plus 7x. This is be careful, because this is a fifth degree equation. These are not in order. They're not in descending order. Sometimes problems will be given to you where they're not in descending order. So make sure you look at all the exponents. We have a 2, a 5, and a 1. So the biggest number is 5. So this would have at most 5 zeros. And at most 4 turning points, or 4 turns. Oops. Yeah. Yeah, I can't write turns. So now now I want to talk about probably the most important topic, and that is end behavior. So we're going to talk about end behavior. So what I mean by end behavior is, how does my function behave at the ends? So at the ends of my graph. So if I have a function that looks like this, and I can have a bunch of bumps in there, and I'm going off to infinity in both directions. So you can see this is a polynomial function. My end behaviors, the only part that I'm concerning myself with right now are these 2 ends. So this is some new notation for us. What we say is, as x approaches positive infinity. So where is that? As x gets increasingly large, as x approaches, right, this is positive infinity on this end, and this is negative infinity on this end. Oops. Can't draw very well. This is negative infinity way out here, right? So as x approaches positive infinity, as I continue to get larger and larger, what is happening to my function? Well, my function is getting closer and closer to positive infinity. So what we say is, as x approaches positive infinity, then my function p of x approaches positive infinity as well. And then if we look at this side, because there's 2 end behaviors, right? There's 2 arrows. Then likewise, we say, as x approaches negative infinity, p of x also approaches positive infinity. So let's look at this. As x gets closer and closer to negative infinity, I'm getting higher and higher, so I'm going closer and closer to positive infinity. Okay? Let me draw another one on here. So let's say I have a graph that looks like this. So in this one, I would say, as x approaches positive infinity, my p of x is also approaching infinity. So let me write that in green. So I would say, as x approaches positive infinity, p of x is also approaching positive infinity. But as x approaches negative infinity, then p of x is approaching negative infinity. Okay, because as p of x is getting bigger and bigger, I'm getting closer and closer to positive infinity, but as p of x approaches negative infinity, as I go down on this line, I'm getting closer and closer to negative infinity. Okay? So there are some, if you can recall your basic functions. So let's go back to some functions we learned last chapter. So do you remember if I had p of x equals x squared? What is that? And then also p of x equals x cubed. If you recall these functions, x squared looked like this, and x cubed looked like this. Remember those from last chapter? So hopefully by now you're looking at this going, okay, my end behavior, I'm getting, as I approach positive infinity, I'm getting closer to positive infinity, and as x approaches negative infinity, my function is getting closer to positive infinity as well. Okay? So the nice thing about this is if you look at this function, this is an even-powered function, right? This has a power of 2, which is an even number. And this one over here is an odd function. Okay? So the end behaviors are going to be the same for all even powers. So as if I have p of x where x is to the 10th power, that is an even number. So what's going to happen in this function is that my end behaviors are going to pretty much be the same. So I'm going to put my end behaviors on first, and then I can have a whole bunch of bumps in between those two graphs, and they would connect. Okay, and later in the chapter we're going to spend a lot of time talking about what's going on here in the middle. So I'm going to put a little box around that, because right now I'm just talking about the end behavior. So all I'm really focused on is where these two tails are going to be, where the two tails are going to be. I don't really care about all the bumps in the middle right now. So if I have an odd-powered function, the nice thing is that all odd-power functions also behave very similarly. So if I have p of x equals x to the 7th power, I am going to be going down this way and up this way. So when I draw my graphs, I usually draw those first. I kind of draw them out on my graph. And then later, we will spend a lot of time figuring out what bumps are going on in between and how they connect. Okay? But right now, what I need you to be worried about, I'm not so concerned about what's going on in the green box. I only want you to understand what's going on with this end behavior. And then the last thing the last thing we have to talk about are negative exponent, or negative powers. So if my p of x equals negative x squared, do you remember what that looked like? Well, that function was that was an upside down parabola. So my end behavior, so if I have p of x equals, say, negative x to the 16th power, well, that is going to, my end behavior is going to be the same, right? I'm going to be down here and down here, with a whole bunch of bumps going on in between. Okay? Again, if I have an odd power, so let's say p of x equals negative x cubed, hopefully you remembered that graph looked like this, right? So I'm only concerned with what's going on at the tails, right? So if I have an odd-powered function, so let's say p of x equals negative x to the 7th power, well, my end behavior is going to be the same. So I'm going to be going off this way and down this way with a whole bunch of bumps in between. And that's about it.